All right, good morning. So today we're going to talk about the experimental user study or user experiment at last, which might be the most likely the case that you might want to do for your thesis, since it's more, I would say, more formal or more tended to describe new findings based on statistics. So let's try to cover how to do a user experiment. So if you remember what we've been talking about in this stream of lectures, we've been talking about how to do user studies based on your research questions. So the first thing we talked about was how to start your plan for your user study based on your research questions. And the more specific, it's more better because it will make it easier to choose what kind of user evaluation methods you will choose and how you will plan for your user study and how it will be easier for you to run user experiments that could make conclusions out of statistics results. So the more specific you have your research questions, it's easier to do experimental investigation or experimental research, while other research questions that is more abstract and more at the higher level, you'll end up more like an exploratory investigation or descriptive investigation where you observe or find new findings through observing people, how they do it. So we've talked about different types of research methods, which is basically a type of user studies we can do. And today we're going to talk about the user experiment, which is at the very bottom of this list. And most of the time, most of the cases, most of the methods up here are for descriptive or explorative investigation, while the user experiment is for experimental investigation, which its name reflects. Of course, I'm not saying that you cannot use questionnaires in the user experiment. It's just saying that survey as a main research method might be more descriptive rather than experimental. So in that sense, if you think of a user study, in any kind of user study, we start with setting a goal, kind of research question, and then we find users to try out the user interface we are studying, and then we collect the feedback, either qualitative or quantitative feedback, and then analyze it and try to answer the research question. And while we think of how we let the users try out the interface, there comes the main difference between other exploratory study versus the experimental study. So exploratory studies usually involve only one type of interface. So you are trying to discover more and understand more about that specific interface. But compared to that, experimental study tries to compare between different interfaces. That could be a state-of-the-art interface that is widely used compared to your newly designed or your new proposed type of interface. So experimental study usually compares two or more alternatives and try to compare between them and see if there's any difference, especially statistically significant difference between the conditions, so that you can say the one you've proposed is better than what is widely used these days. So in terms of that, we have to learn a couple of new words, or you might be already familiar with those terms, such as independent variable and dependent variables. And by independent variables, we mean the treatments or conditions you'll have differently between. So independent variables is those you control so that you make different conditions to compare. And dependent variables is usually what you measure, so such as task completion time or usability level or something like that. So we'll go into more details about those two variables later on. So in essence, how your user experiment flows is, so user experiment, experimental user study usually are also called user experiments. And how it differs from other type of user study, it's first of all, it's hypothesis driven. We'll talk about what hypothesis is, but for now we'll say it's a kind of a sentence that defines what your expected findings are from your user study. And then through the user experiment, you either reject or retain the hypothesis you made so that you can make conclusions of saying your hypothesis was correct or your hypothesis was wrong, and so forth. And usually it compares multiple conditions, as I've mentioned earlier. And although you can also collect qualitative measures or feedbacks, it usually involves quantitative measure so that you can do statistics based on these quantitative measures, and so that you can make conclusions out of it. And it also tries to remove bias and error. So you try to control all the other error sources, such as environments that you do the experiment. If there are some unexpected noises like this, then users might be affected by those noises. So you try to control all those kind of error sources and biases and make sure only the controlled independent variable you are controlling are causing the results. So you try to remove bias and errors. And as a part of it, you do random assignments because there could be some factors that you cannot really control. So what you do is when you recruit the participants, you randomly assign them to different conditions and different groups so that those unexpected random errors could be balanced out by randomly assigning to different conditions. And in essence, as you try to, all of these efforts are because of trying to make it more generalizable, so that the conclusions you found from your user experiment, which is a small sample of people or participants, to make it more generalizable in different cases and different situations, so that it could, if somebody does the similar experiment, then the results should come out similarly. In that sense, it should be replicable. So what you go through when you are doing a user experiment, so this is kind of a flow, what you usually do. First, of course, you start with the research questions. In this case, for the user experiment, usually research questions are formulated out in a more formal way, which is called hypothesis. And it's basically, in an essence, a prediction of the outcome, how your outcome would be. And usually, this hypothesis describes the relationship between the independent variable, which is basically the conditions you have, and how the measurements, such as task completion time or usability scale level or sort of things, would differ between the conditions. So the hypothesis usually describes those. And then once you have that hypothesis, then you run an experiment. Of course, you'll have to carefully plan for what kind of task you're going to ask the user to do, or what kind of conditions you're going to let them go through, and what kind of environment you'll put them in, and how to measure all of those dependent variables and so forth. So you carefully plan for the procedure and run the participant through that procedure. And once you've run the experiment, then as an outcome, you'll have a bunch of measures depending on different conditions. And then you do run a statistical analysis around that quantitative measures and test if your hypothesis was correct or wrong. So, for instance, if you set a hypothesis that people will have different test completion time between using mouse and a stylus pen, then your hypothesis could be either rejected or supported through the findings you've measured through your experiment. So you'll be measuring test completion time for each participants under different conditions, and then you compare the mean value of the test completion times with statistics and see if that's meaningful or not, or in terms of statistical significance, which is based on probability. And then you can conclude either stylus and mouse is really different in terms of test completion time or not. So going into more details about making hypotheses, first we'll have to know about what our independent and dependent variables are. So independent variables are the factors that the researchers are interested in studying. And those are possibly the cause of the change in the dependent variable. And in that sense, it's independent of a participant's behavior. So mouse and stylus doesn't depend on how user behave. So it's given to the condition. So that's why it's called independent. And usually the treatments or conditions, so such as type of interface you are using, is independent variables. And dependent variables are outcome of the experiment or what you are measuring usually. And that depends on what the users are given, what the conditions users are given. It will be depend on what kind of interface they're using. So such as test completion time might be depending on what kind of interface you are using. So that's why it's called dependent variables. So more of an example of independent variables. So basically, many of the cases, type of technology or type of interface will be one of the type of independent variables. Of course, you can have more of a subcategory, such as type of pointing devices versus type of audio, visual interface, and so forth. So you can have more subcategories. It has to be one category. There are also other type of independent variables that are related to users, such as age group, such as younger participants, older participants might have different test performance, or gender, or other cultural or educational background could be also work as independent variables. But this is only the case when you are interested in looking into difference between these groups. So if you're not interested in how people perform or how people think of how usable your interface is depending on age group, then you don't have to choose it as an independent variable. So all depends on what is your research question. So if your research questions involve something like how your interface is more accepted to younger generation than the more elder generation, then you might put one of the independent as the age group. But if your research doesn't have interest in comparing different age groups, then you don't have to. And other type of independent variables, other type of context could be physical status, user status, or social status. Some of them, actually many of them, again, relates to users' background or users' status. But any type that you want to compare between them, you can think it is an independent variable. So typical dependent variables, I think we've talked about this a bit earlier when we were talking about the usability testing. So you can think of similar measures such as efficiency, including test completion time or speed of people doing things, or how accurately they did, or how satisfied were they in terms of usability, such as how easy was it, how easy was it to learn, or how intuitive was it, and so forth. You can do Likert scale ratings and so forth and use it as a measure. So that's dependent variable. And other things you can think of physical or cognitive loads, such as how stressful was the interface while they were using in terms of physical ability or cognitive load and so forth. And we talked about some questionnaires that can measure this, such as NASA TLX when we were talking about questionnaires. So, and there are also other types of variables in experiments. So independent variables are the different conditions that you want to compare. Dependent variables are the measures that you are testing to see the difference between the conditions. And there are also other type of variables, which is controlled variables, or sometimes also called constant variables. And that's not your interest of your research question, but those variables are set to a constant value to make it more even, or more make different conditions more equal and fair for comparing. So examples could be such as noise level. So for instance, if you are not controlling the noise level and some of the participants had done the same task in the very noisy environment and some of them did in a very quiet environment, then you weren't interested in how people perform under different noise level, but it's better to control it to a same level so that it will not affect the results. And by controlling as much of the variables, you'll get more internal validity, which means the conclusions you have is due to the independent variables, not because of random errors. But as you control more of the environment, it has a side effect of having making it less generalizable. Because, for instance, if you are going to test an interface for bike navigation, let's say, then if you test it inside a very controlled test environment, such as a laboratory, then it might not reflect the real environment they use the interface. And too much of a control might make it less generalizable to real situations they use the interface itself. So you'll have to think of, you'll have to control the variables as much as possible, but you might also be careful if you're controlling too much, that makes the study too much controlled and make it less generalizable. So it depends on the type of the study or type of the situation you have. So it's up to you. It's all up to you, but it's always good that when you report it in a paper or your thesis, you write up that you control these things because of this reason. Or if you didn't control them, then you can say you wanted to make it more similar to the real world scenario, so that you left those out for uncontrolled variables and so forth. And those variables that are left out, not controlled, are called random variables. So the more of random variables you have in your experiment, then you might end up those random variables affecting your results. So that could be a threat to your validity of your study. But again, it's a kind of trade-off between those two. And also there's another term called confounding variables, which is a type of random variable that actually affects the independent variable, such as so could be a personal background or age group that you were not interested in, such as age group or educational background and so forth. You might not have been interested in, so you didn't identify it as an independent variable, but it might turn out that that was actually the key thing that affected users' task performance. So in that sense, those are called confounding variables, but in that sense, it's a kind of random variable that you might want to control them so that you have similar age group or similar educational background of the participants you want to investigate. So and one of the way to deal with these random variables and confounding variables is to do random assignments. So one way to do is to randomly assign the subjects. So those random variables could be even out between the conditions by randomly assigning people. So giving the same chance to different people with different random variables assigned to different conditions. So in that sense, random assignment is very important when you're doing an experiment. So let's start a little bit more detail about how to plan for your user experiment. So in an essence, user experiment is all about testing your hypothesis. So first of all, when you plan for a user experiment, it's important to identify or define your hypothesis before you start anything else. So hypothesis is a precise problem statement that can be tested through an empirical investigation. So here, within the hypothesis, you should specify two things. I'm not sure why is this unindented. So inside the hypothesis, you should specify both independent variables, which means different conditions you have in your experiment, and also the dependent variables, what you are measuring. So, compared to a theory, a hypothesis is much more smaller statement. So it's usually involving one independent variable with one dependent variable. So if you have more than one independent variable with dependent variables, then maybe you'll have to split out your hypothesis into, sometimes you call them sub-hypotheses, but anyway, you have to split it out into multiple hypotheses. So you might have one hypothesis saying mouse and stylus might have different test completion time. That could be one hypothesis. And the second one could be mouse and stylus could have different level of easiness of using. So you'll have to separate them into different hypotheses so you can test them individually. So in that sense, in your user experiment, it's not necessary to have only one hypothesis, but you can have multiple hypotheses depending on how much of different measurements and how much of independent variables or conditions you have. So you can have more than one hypothesis, but usually you define one main hypothesis, which is the most of your interest, and then you define other hypotheses, additional hypotheses. And proving and disproving the hypothesis. If you need to prove something in an empirical way, if you think a little bit about it, you can easily think it's logically impossible. So, for instance, if you want to prove that all of, let's say, all of, I don't want to be anything about, let's say all of Koreans has black hair. I don't want to get this dispute, but anyway, if you want to prove that through empirical way, then the only way to do is to check all of the population, right? But it's much easier if you want to disprove it, because if you find one evidence of one person having not black hair, then finding only one evidence, you can disprove the statement. But to prove it, you'll have to check if it's always the case. So in that sense, it's easier to disprove something than proving something. So so that's why we come into a concept of null hypothesis and alternative hypothesis. So since disproving something is easier than proving something, the way scientists came up with, instead of proving your hypothesis, you negate your hypothesis and disprove that negated hypothesis, and that's called null hypothesis. So, and the hypothesis you want to support is actually called alternative hypothesis, and this hypothesis is what the researchers want to support. So, for instance, alternative hypothesis could be stylus and mouse has difference in terms of test performance. That's the one thing that you want to support if you have invented the stylus and you want to say it's better than doing things. And that's the alternative hypothesis you want to support. But since it's harder to prove this hypothesis than to disprove it, you make a logical negation of it, which is there is no difference between the two. And you call it null hypothesis. And this is one that you want to reject or disprove it so that you can support the alternative hypothesis, which you really want to support. Okay? So that's why scientists came up with a little bit complicated situation that the thing that you really want to support is called alternative hypothesis, and the negation of it, logical negation of that hypothesis, is called null hypothesis, which you disprove it through your experiment so that you support your alternative hypothesis. And in short way, the alternative hypothesis is usually called H1, and the null hypothesis is usually called H0. And these two should be mutually exclusive. So, for instance, if you set alternative hypothesis as using stylus is faster than mouse, the null hypothesis cannot be there is no difference, but should be either no difference or mouse is faster. Okay? And in some sense, null hypothesis, in most of the case, you end up with saying there is no difference between the conditions or interfaces because the statistics tools available are good at saying if there is a significant difference or not, but you'll have to do more when you want to really say which one is faster than the other. So many of the statistics tools you use, you will end up using, will be able to tell if there is a difference between them or not, but telling which one is faster, maybe you'll have to fall back with descriptive statistics rather than using the statistics, inferential statistics. So usually when you formulate a hypothesis, you formulate the null hypothesis in a way that's saying there is no difference between the conditions. And in that sense, the alternative hypothesis usually becomes there is a difference between the interfaces or even significant difference between the conditions. So for example, if you are going to compare three interfaces, V, Move, and Kinect, and you are doing a pointing task and you want to check if different three interfaces have different task completion time, then the alternative hypothesis, which you really want to say, or say if you have invented Kinect and you want to highlight the good thing of Kinect, and then the alternative hypothesis you might formulate will be there is a difference in task completion time between the three, TV, Kinect, and Move. And then the null hypothesis, which is the opposite of it, should be there is no difference between the tasks. And then you throughout the user experiment, you measure the task completion time, and then crunch those numbers using inferential statistics, which will let you know if there is a statistically significant difference between the two mean values. And then if statistically, if it turns out there is a significant difference, then you reject the null hypothesis. so that you can support H1 is more likely to be true. So in summary, research hypothesis should be clearly defined in terms of it could be supported or rejected. So you can say this could be true or false statement. So it should be clear in terms of that way. And it should be have appropriate scope. So it should have identify what are the independent variables, what are the conditions, and what are the dependent variables, what are the measurements you are really comparing to compare different conditions. And in that sense, for planning the user experiment, independent variables should be easy to control. So if the independent variables is hard to control, such as I can't think of an example for now. But if you think the independent variable you choose is hard to control, then you can easily think you can not really replicate the situation easily. So the independent variables should be easy to control. And the dependent variables, of course, should be easy to measure, or there should be an accurate way to measure it. Otherwise, it might be hard to compare the measures. So once you have that hypothesis set, the goal of the experiment is to either reject or retain the null hypothesis using statistics tools. So in essence, is to find a statistical evidence through your experiment to either refute or reject the null hypothesis so that you can support your alternative hypothesis. So, but again, here comes the limitation of statistics. With statistics, you cannot really prove or disprove the hypothesis. So you can only statistics always lies on the theory of probability. So there it's all about saying the chance of being able to reject or retain the hypothesis. So you cannot really disprove it or disprove it. But in that sense, you cannot really say you proved or disproved your null hypothesis, but you use different term or word called reject or retain. Rejecting your null hypothesis is saying that your hypothesis is not true, seems to be not true. I mean, with high probability, it's not true. So that's saying rejecting. Or retaining is saying with high probability, it seems to be true. So you either reject or retain your null hypothesis to support or reject your alternative hypothesis. So be careful of using the term prove or disprove being your hypothesis. So some picky reviewers might say you don't prove or disprove your hypothesis using statistics. You always can only reject or retain. So those are the terms that you use for saying if you reject or retain your hypothesis, but not prove or disprove. And whenever you use statistics tools, which is based on probability, there is a chance that you might have concluded in a wrong way. So you made a wrong conclusion. So since it's based on probability, statistics are based on probability, there is a chance of making errors of your decision. So there are two types of errors. If you think of this two columns is saying in reality, let's say there is no difference between the two interfaces, and this is a case where there is a difference in reality, and this is what you made your decision based on statistics. So if you, based on statistics, if you have rejected your null hypothesis, even if in reality it was true, then you're making an error. And we call this type of error type 1 error. And this is sometimes called false positive. And there's also the other way around, where in reality the H1, your alternative hypothesis is true, but you, based on statistics, you retained your null hypothesis because you didn't find statistical evidence. So in this case, this type of error is called type 2 error, and this is sometimes called false negative. And the probability of making this type 1 of error is called alpha level. And probability of making type 2 error is called beta. It might sound a little bit complicated, but we have to know this one is called alpha and the other one is called beta because of we'll be using this term when you run statistical tools. Okay, but in many cases, statistical tools are mostly interested in this alpha risk because of saying there is a significant difference between the two interfaces is more riskier than finding no evidence of difference. So if you propose a new interface and you want to claim that this is much better than the state of the art, scientists think that it's much more riskier to approve it is better than finding it no advantage, even if there is actually an advantage. So it's being very careful about approving the new ideas or new findings, I would say. So as you can see through all of the themes we are talking today, it's being very careful and conservative of approving new findings, okay? So many of the statistics tools and the scientist community and through the user experiment, you'll mostly trying to minimize this type 1 error, which is saying there is a significant difference, although there is actually no difference, okay? So if you think of an example of, this is not an example of HCI field, but if you think of a diagnosis tools, let's say you've invented a diagnosis tool that can identify if someone has a flu or more serious disease. And in reality, if someone is not having a flu, but if you decided he has a flu or he or she has a flu, then it's a false diagnosis, right? It's a false positive. And this is type 1 error. And type 2 error is in the case he is actually having a flu and not saying through your testing method, you say having no flu, then this is not detecting the flu, which is false negative. And if you think of the relationship between these two, if you make alpha, which is probability of making type 1 error, if you try to make it low as much as possible, and if you as more you make the chance of making type 1 error lower, you are making the chance of false diagnosis lower, but in the other way around, you're also making the chance of not detecting the flu higher. So these two are dependent with each other. So if you try to make type 1 error happen much less, then you might increase the probability of having type 2 error. So saying that, the point is alpha and beta, which are the probability of making type 1 and type 2 errors, are interrelated. And in experimental research, it's generally type 1 errors are more worse than type 2 errors. And in a sense of being more conservative about your findings. And so usually the alpha level is set to very low value, which is 5%, which is 0.05. And this is usually the value that is the threshold or the bar that your finding has to meet with based on your statistical findings. So let's say your alternative, your null hypothesis was saying no effect of the solution, which is by meaning effect is being effective of lowering your task performance or increasing your, increasing your task performance, such as lowering the task completion time or reducing the error and so forth. So say that your null hypothesis is having no effect between the conditions or your solutions. Then testing the hypothesis in essence is testing if whether the effect is too large to likely have occurred by chance. I think we'll have to unfold it a little bit. So by effect, we are meaning the difference between the two measures, such as task completion time. So we are trying to find the probability of finding the difference between the two with your sample, which could be depending on the chance of sampling. So if you have, from the population, if you have sampled this group, then you might have found this much of difference. But if you have sampled different group from the population, then you might have found no difference between the two conditions, right? So the p-value or the probability value of your statistics test is saying the chance of finding difference between the two groups, two conditions, although there is no statistical difference. So I think this actually summarizes what I said. So the p-value or probability value, which is usually given out from the statistical tool, is the value of a chance that's assuming the H0 is true, which means there is no difference, is true in the population. The probability of observing a difference in your sample. So in essence, p-value is based on your participants, and you ran the study and you crunch the number with the statistical tool, and it will print out the p-value. And what p-value means is the chance of making type 1 error, which is saying there's no difference between the conditions. And if this p-value printed out from your statistical tool is lower than alpha, which is 5% usually in HCI field, so if there is a less than 5% chance of saying there is no difference between the two, then you can say it's too low probability that you can retain your H0, so you can reject H0 to support H1, which is alternative hypothesis. Okay, so in an essence, alpha level is usually set to 5%, which is 0.05, and you run the statistics tools, and if the p-value printed out is less than 0.05, then you can reject H0 and say your H1, which is usually there is a difference between the interface is supported. And by the way, this alpha level is in convention usually set to 0.05 or 0.01, but 0.05 is more widely used, I guess, I think. And also this, and the point is your printed out p-value based on your measurements. The point is to check either it's less than this or not. So having a p-value of 0.0001 and having a p-value of 0.04, both are significant difference. So you can say both are significantly, statistically significantly different. But you're not saying one is more significant than other. You don't use that kind of description, although the values are different. You don't really say that. You only say if it's significant or not. So it's true or false rather than value. Okay. So for example, if you say your null hypothesis was there was no difference between task completion time for V and Kinect, and you ran the user experiment and measured the mean task completion times, and we came up with the mean value of 10 milliseconds, and Kinect came up with the average 500 milliseconds to complete the task. And you can say the difference, time difference between the two interfaces was 400 milliseconds in average. But to say if this difference, this 400 milliseconds of difference is statistically true and not by chance of sampling a certain group of people from the population, you run a statistical test. In this case, you can use t-test, which we'll cover it later in another lecture. And you run this statistical test, and the test printed out p-value of 0.04. Then, since it's less than 0.05, which is commonly accepted alpha level, which is, then since it's lower than 0.05, you can say the difference you found, it's not by chance, but it has very low probability of finding no difference, although if there's a difference. So you can, the probability of this finding a difference of, for finding this much of difference, even if the actual population doesn't have a difference, is only 4%. So in that sense, it's very low probability. So you can say H0 is appear to be not true. So you can reject the H0. And then by rejecting the H0, you are actually supporting H1, which is saying there is statistically significant difference between the two. But again, this is based on statistics, so it's just about probability is very low of saying that there is a very low probability of H0 being true, so you're accepting the alternative hypothesis. And but you have to be careful of statistical significance being meaningful for your study or not. Because even if it turns out statistically significant, between the difference being statistically significant, it might not be that much of difference be meaningful. For instance, we've said the difference of 400 milliseconds. If it's a gaming interface, then the difference of 400 milliseconds of task completion time, although it's statistically significant difference, it might not be that important as a gaming device. But if it was an interface that was kind of a brake system in a car, then that much of a, even if it's a small difference, it could be meaningful, right? So statistical significance is not exactly meaningful, exchangeable of being a meaningful difference. Being a meaningful difference depends on what is your study about and what's the context about the whole story. But still, statistical significant difference is still, even if you had, let's say, like 10 seconds of difference in terms of comparing the average value, but if it turns out not statistically significant, then is that a meaningful difference? Even if?
Sorry, can you?
So in the other way around,
yeah.
If you measure something and in average it had 10 seconds of difference in terms of text completion time, and 10 seconds is quite a lot in your scenario, but by running your statistics tool, it printed out higher than 0.05 probability, since it's not significant difference. Can you conclude that 10 seconds is meaningful?
You said 0.05 is the acceptable time.
Mm-hmm. Yeah. So it's above it. So even if the mean values are different by 10 seconds, it's still, you cannot claim that the two groups had a difference statistically, because that 10 seconds might have happened. The reason why statistical significance level was higher than 0.05 was that the reason of observing that much of difference might have been because of sampling a biased number of people from the whole population. So that difference might not be because of the different condition, but might have been because of other source of errors. Okay?
So then what can you do? Because aren't you supposed to try and get above 0.5?
You're trying to get below 0.05. Below 0.5 because the p-value is probability of
making it hard. One error.
I'm even confused. Yeah, so as here, p-value is assuming H0 is true, assuming there is no significant difference. P-value is probability of observing a difference. Okay, so anyway, first of all, you check your p-value through statistical tools and make sure the difference you've observed is not by chance of other error sources. And once it's significant, you still think, once it's statistically significant difference, you still have to think of if that amount of difference is meaningful to your scenario or not. And the other pitfall is, even if you didn't find significant results difference between the two groups, you cannot say those are equivalent. Okay? Saying equivalent is another thing, which is, if you want to say equivalent, then if you go back to first setting the null hypothesis and the alternative hypothesis, the way you did was you put your hypothesis that you want to support in alternative hypothesis, and you made a null hypothesis by making an opposite of it, and you tested that null hypothesis using a statistics tool, right? So if you really want to say the two interfaces are the equal, then that becomes a alternative hypothesis, and your null hypothesis is there is a significant difference between the two, and there are different tools that statistics tool that you have to procedures that you have to go through to check if those two are actually equivalent or not. So anyway, in essence, if you find no significant results, which is p-value being higher than 0.05, then you can say there was no significant difference found from your experiment, but you cannot conclude there is no difference between the two in the whole population. Okay. All right. So I think I had a question of. So let's do a little bit of exercise. So say you are going to compare. You've invented a very nice 3D pointing device, and you want to compare it with state-of-the-art 3D pointing device. Say we have what we have in the lab in the vision space, and you want to compare those two, and you're comparing the accuracy of it, and what do you think will be the H1, which is easier to do? So what would be the alternative? Let's say just interface A and B. So H1 should be.
So there's a new pointing device which is a 3D one. So you're comparing the current one in vision space with a new one. So what is the new one like?
New one, let's say it's A. Interface A is the new one, and interface B is the existing one. And then the hypothesis should say you should include the independent variable. So you should say between A and B.
Yeah.
And then you should also include dependent variable. Yeah. There is a difference between A and B in terms of accuracy of pointing. So that will be H0, H1, which you want to support.
Between A and B, there's a difference in accuracy.
Difference in accuracy. That will be H1. And for null hypothesis, you just negate it. So saying between A and B, there is no difference between A and B in terms of accuracy. So that will be your H0. All right. So that's kind of the very beginning of your experimental design, setting your hypothesis. But I think that's a very, although it's a very starting point, it's a very an important step that defines the whole of the rest of your experiment design. So I think that was.
How many options can you have in a hypothesis when you're defining it? So you can have, for example, the
3 interfaces and so forth. You're comparing 3 interfaces.
No. So for example, when forming your hypothesis, for each of them, can you have multiple options? For example, in the example that Jonathan just gave, he said difference. So that's the option. That's the option that we have, the independent variable. Is that right? So
independent variable is type of interface. Interface A and B, that's independent variable. Dependent variable is the measurement, which is accuracy.
Yeah, accuracy.
Or test completion time or whatever you measure.
Yeah.
So ideally, hypothesis should be rejected or retained by itself. So usually you end up, as I mentioned earlier, you have to divide the hypothesis into multiple hypotheses, which might end up with containing one independent variable and one dependent variable.
Okay.
So if you want to say, such as, again, comparing interface A and B, and if you want to compare task completion time, accuracy, and usability level, then you'll have to have 3 hypotheses. One saying A, B is different in terms of test completion time. The second hypothesis you have would be A, B different in terms of accuracy. The third one will be A, B different in terms of usability level.
Okay. So that's the dependent variable that is changing.
Yeah.
What about the independent variable?
Independent variable also same wise. So if you have 2 independent variables, one is type of interface, and the other one you are also interested in the age group.
Okay.
Say younger people are better with using interface A, older people are better with interface B, and so forth. If you want to do that kind of multiple independent variables, then you'll have to divide them usually into one for each independent variable.
Okay.
So in that sense, you are having saying that there is only one measurement. Again, you'll have to multiply it by the number of measurements again. But anyway, you can have one hypothesis per independent variable, saying interface A and B will be different in terms of test completion time, and the age group 1 and 2, or younger group and the older group, will have difference in terms of test completion time. And then here comes another factor, which is the interaction between the two. So usually if you have more than one independent variable in your hypothesis, you end up with one hypothesis for each of the independent variable, and also one per each of the pair. So saying, because that depends on, it depends on what kind of statistics tool you end up with using it, but it's called the interaction factor between the independent variables. So I think I have a slide later on saying how you formulate them. But basically, one per each independent variable, which is the main factors, and then also one per each of the combination of the two. So in that case, it will be so the interaction factor, the hypothesis could be test completion time could be different in terms of interface A and B, depending on the age group and so forth. So although it's ideal to write out all of the hypotheses, usually you end up with kind of playing in a little bit more higher level. So usually you end up with playing with little bit of higher level, saying, for instance, you are measuring, at least in the writing level, in the report or in your thesis, you usually put your hypothesis in a little bit more higher level, saying interface A and interface A, B have let's say interface A and B are significantly different in terms of test performance. And as a measure of test performance, you might have test completion time and error, and number of times they failed or so forth. So you can have multiple measures representing the test completion time. And by looking into these different measures, and of course with statistical test, you'll have to run them separately. Test completion time in one statistical test, error in another test, and so forth. And if you found significant difference between these types of measures, and then you kind of make a conclusion out of summarizing all three of them. So in a report, you usually don't mention each of the hypotheses. But in an ideal case, if your study is simple enough, then it's more ideal to write it down, what actually the hypothesis you are testing against. So so far we've discussed about how to set your hypothesis, which is the main goal, to either reject or retain the hypothesis through your experiment. And then you'll have to think of a little bit more detail about how to run the experiment. And designing an experiment involves many different decision-making process. First, you'll have to decide your variables, which you might have already done while you were formulating the hypothesis. And based on this independent variable, you might also think of how many conditions you'll have to let the users try, and what will be the experimental task that you'll be asking the users to do to measure the dependent variables, and what kind of environment you are going to let them try those tests in, and what will be the procedure, in what order you are going to let them try each conditions, and how you are going to assign the participants to them, how many participants you want to run through, and in overall, while doing all of these, trying to avoid bias or errors that could be introduced that might lead into wrong conclusion. So independent variables and conditions are slightly different because independent variables are, so if you're comparing two interfaces, there are two conditions, one condition using interface A, the second condition using interface B, but the independent variable is only one, which is type of interface, okay? So think of variable, it's like in computer science, it's a variable that you can put different things, right? So even if you have three conditions having three type of interfaces, interface A, B, C, there are three conditions, but still it's one independent variable, which is type of interface using, okay? So what you'll have to decide is not only the independent variable, but how many different conditions or levels you will have with one independent variable. So if you say you had three interfaces, A, B, C, and you had two different age groups, such as old, like teenagers and elder people, then you can think of there is two independent variables. One is type of interface, and the other is age group. And the first independent variable, which was type of interface, has three levels, right? So interface A, B, C. And the second independent variable has two levels, which is younger or older people, which is divided into two groups. So, and if you think of how many conditions you'll have to test with three levels in one independent variable, two levels in the other independent variable, then it's basically multiplying those two numbers, right? So you'll have to test, you'll end up with having 6 different conditions of two independent variables with different number of levels. So in a simple experiment where there is only one independent variable, the number of conditions is exactly the same as number of levels or conditions within that independent variable. But if you are interested in more than one independent variable and how they are interrelated with each other, then you'll have to multiply each of the number of conditions in each independent variable. And in that sense, the more of independent variable you have, it multiplies the number of conditions you have to let the users try. So with our previous example with having 3 by 2 conditions, you actually call the design of your user study is 2 by 3 or 3 by 2 factorial design. So this is saying the first independent variable has 2 levels. Maybe this is the age group, and the number 3 represents the second independent variable has 3 levels. And if you had another independent variable, you can end up with 2 by 3 by 4, or 2 by 3 by 2, or 2 by 2, or whatever combination you have in terms of number of independent variable and levels within each of them. And saying of that, so also with these different conditions, usually one of the conditions becomes a control condition, which is usually representing the state of the art. So you call that condition controlled condition, and the other conditions, experimental conditions, which is what you've introduced newly and tried to compare against the state of the art. So when designing a study, you first try to identify the independent variable, which is if you are interested in only type of interface, then that's only one independent variable. So if you have only one interface, one independent variable, then that's called basic design. And if you have more than one independent variable, then it's called factorial design, as we've talked about earlier in the example saying 2 by 3 factorial design or 3 by 2. And then within the basic design where there is only one independent variable, you still have to determine the number of conditions. Even if you have only one independent variable, again, you can have more than 2 or 3 interfaces, type of interfaces you're comparing. And within the factorial design, you still, again, define the number of conditions by multiplying the levels or conditions within each of the independent variables. And then once you have identified all of those conditions that users have to try, then you come with faced with how to assign each of the participants to each of the condition. So one way is to let each of the participants try all of the conditions. So each of the conditions trying all 6 conditions is called within subject design. And the other way to do is if you have too many conditions, then it might be too much stressful for one user to try all of them. So you can actually assign one participant to try only one condition, and the other participant to try another condition and try to run statistics out of it. So in that case, each participant trying different conditions is called between subject or between group design. And sometimes it's called also within subject or within group design is also called correlated samples or paired samples. And between group design, which is each participant trying different conditions, is called independent samples. And these independent and correlated samples are usually, depending on what kind of assignment you use, will end up with different statistic methods you use. So some of the statistics methods are for independent samples, and some of the statistics methods are correlated samples. So it's important which assignment you use ends up with different statistics tools you use. So if you think of cons and pros of each of the methods, if you assign each So first within subject, where you let each of the participants to try all of the conditions, it will need longer time for each participant, right? And since they are doing the same test with different interfaces, they might cut with learning effect, which means they might learn how to do the task while for the first conditions, they might have been not familiar with the task, but as you try out different conditions, they might learn how to do the task and you might perform better as you do the later one. So that's a side effect of letting them try different conditions together. But the between subject, on the other way around, it will take shorter time for each participant, and also can avoid interference with the learning effect. But on the other way around, with letting different subjects, using the within subject design, you can isolate out the difference between the participants, each participant. So for instance, participant A could be quite good at doing the test. So while participant B could be quite bad at doing the same task anyway. So there could be some difference between the participants as well. So by letting each of the participants do all of the tests, you can compare the values within that participants did between the conditions. So you can isolate out the difference between the individuals when you do the within subject design. So in that sense, usually within subject design requires a smaller number of participants compared to between subject, which is more vulnerable to variation between the subjects, and you might need more participants to have statistically significant results. But in some sense, some of the independent variables only can be between subjects, such as gender or age. You cannot really make it within subjects because you cannot change your gender of your participants during the experiment. And on the other hand, some of the independent variable could be only within subjects. For instance, if you want to measure change over time, such as how people perform better when as they tried the interface multiple times, then that factor should be within subject because that involves learning if you are measuring such as how easy it was to learn using this interface, then it might involve people have to try multiple conditions as a within subject design. So as we can see here, between subjects are more vulnerable because of the variance or error between the individuals. So it becomes more important to randomly assign the individuals with different conditions, right? If you have assigned with some intentions a specific participant to a specific condition because of you thought that participant might perform quite good with this interface, then you are introducing bias with that assigning. So it's very important to randomly assign each participant to different conditions. In comparison, within subject, you are letting them try all of the conditions, so you cannot really assign them randomly to different conditions. But what you can do is randomly change the order of the condition they experience. So if you had 3 conditions A, B, C, and the first participant tried it in an order of first trying A, B, then C, then the next participant maybe will better experience that in different order, such as B, A, then C, in such a way, so that it will counterbalance the learning effect due to the order they experience each of the conditions.
Is that why most experiments in HITLab are within subject?
The reason why many cases you prefer within subject is because it requires smaller sample size. So that's one of the reasons why people prefer within subject design.
And if you're comparing, so say for my own, if I was to do rehab of games to improve physical therapy, would I be able to use existing data? So rather than have like 2 groups, a control group which does normal rehab exercises,
Mm.
but they have just take the existing data that people have gathered from doing those exercises normally, and just compare it against my data that I'm getting from rehab games.
Could be. Yeah, could use existing data. It might be less convincing the reader because it might have been influenced by different error sources, such as even though so the conditions might have other. The existing data could have had other factor that affected that results other than the new interface you've introduced. So it might not be an ideal case, but still you can say that this is kind of existing data and you compare it against it. You can still run statistical significance between them and make conclusions. But it's better to do a full experiment of having two conditions because in that way, the more you control, you're reducing the number of chance of errors that could be introduced by other factor than the interface you actually try to compare. So that's the case. And then by counterbalancing for the within subject design, again, the order of the interface they try could be quite important, and it's better to make it balanced out to have even number of different combinations. And in that sense, this design balanced Latin square method is also introduced in within subject designs. Balanced Latin square is a kind of mathematical matrix where each of the item comes only once per each row. And so this is an example of 3x3 Latin square. So it's, as you can see here, A, B, C comes once only for each row and each column. So A only appears first at the first column, B, C. So the reason why using Latin square is if you use all of the permutations of possible order, then it could be quite high number, right? So if it's 4, then it's actually 4 factorial, that different combinations of order that you end up with, which is almost like 24 cases, like. But with Latin square design, you can still make sure each of the conditions comes at each place of the order. It always comes first place, second place, and third place. And also with the balanced Latin square, it's also balanced with each items occurs with the balanced Latin square, each condition precedes and follows each other conditions only with the equal number of times. So for instance here, A always comes before B for 2 times, and if you compare A and B, A comes before B for 2 times with first row and the fourth row, and it comes after B with 2 rows. So it balances out between the 2 conditions as well, not only where it comes in the whole sequence. So in this way, still you can argue that it's less balanced than trying all the permutations, but you can still say that this is reasonably well balanced to balance out the side effect of having learning effect between trying different conditions in different orders. So, and that's saying about random assignments, and I think I've explained quite a lot about it. And random assignment is quite important for between subject design, and it's one of the characteristics that you decide if your experiment is a true experiment or not, a quasi-experiment. So when you design a user study, if it has, again, multiple conditions, then it's a type of experiment. If you are only investigating one interface, then usually it's a non-experiment. It's a user study, but it's not an experiment. But even if it's an experiment comparing multiple conditions, If you use random assignments, then it's called true experiment. But it's somehow, some reason you are not able to randomly assign them, then it's called, there's another term called quasi-experiment, and it's an ideal case, I would say. So if you sum up all of what we talked about between subject and within subject design, between subject design, you randomly assign them to different conditions. You have, like, if you have 12 subjects and you have 3 conditions, then 3 subjects tries condition 1 and collect the data. 3, no, actually, it should be 4, right? 12 subjects, 3 conditions, yeah. 4 subjects tries this one and collects the data. Another 4 tries condition 2. Another 4 tries condition 3. But the way you assign each of the participants to each condition should be decided randomly. Okay? So by random, you can throw a dice or whatever, or do a random table or whatever. So, and within subjects, you still do random assignments, but here, it's not assigning each of the participants to each condition, but it's assigning to different order of conditions. Okay? So this order is, again, this, you can define them based on the Latin square design. So here you can see the first case is trying condition 1, 2, 3 in this order. The second case is trying condition 2, 1, 3 in this order. The third one is trying 3, 1, 2 in this order. And you randomly assign this. Still, you'll have to randomly assign the subjects in to different orders. So sometimes you can be tempted to think that this participant might be perform well when they try condition 2 first and then try 1 and 3, so that you assign that person into that order. Then that's not the way how to do it. So it's always important to randomly assign them to be a correct way to do a true experiment. So far we've been talking about only one independent variable. If you have more than one independent variable, then it's called a factorial design. Well, in comparison, if you have only one independent variable, it's called simple design or basic design. If you have more than one, it's factorial design. And in some cases, both of the independent variable could be both between group or both within group. But some cases, you might have to mix them. So for instance, if we had different interfaces as one interface independent variable, and the other one was age group, then interfaces could be within group design, but the age group cannot be within subject, right? So should be always between subjects. So in this case, it's kind of mixed design. So this is called mixed design, having some of the independent variables as between group and some of the independent variables as within group. So this is called mixed design. And in the HCR research methods book, it's called also split plot design, which is not widely used term, but anyway, our book calls it split plot. So if you're, for instance, if your experiment had two independent variables, interface and skill level, and each of the independent variables had 2 levels in it. So interface, there was 2 level. Skill level also, there was 2. Then it's called 2 by 2 factorial design. Okay. And as we've discussed earlier, as Mo raised the question, if you have more than one independent variable, then usually you end up with testing multiple hypotheses, one for each independent variable, and one for each of the combination of the independent variables. So for instance, if it's 2 by 2 factorial design, you test first one hypothesis, which is mainly affected by the interface. And the second hypothesis will be mainly affected by the skill level. There's a difference between the skill levels. And then the third hypothesis will be the combination of the 2. So let me show you this. And this combination of the 2 is called interaction effect. So interaction between the 2 independent variables. And this is this interaction effect is becoming having a difference depending on the other independent variable. So for example here, if you're comparing a mouse against a touch screen, so that's one independent variable of type of interface. And if you're also comparing the novice users against the experienced users, then and you plotted a design the outcomes. Of course, these are average values of your subjects. And if there is a interaction, which means the results changes depending on the other independent variable. So in this case, touch screen. So this is the number of targets selected per minute. So higher the number is better. So touch screen performed better than the mouse when it's novice, but when it was experienced users, it reversed, right? And if you want to say this is a significant difference made by between the novice user and experienced, again, you can still check if so although if there is 4 conditions, you can still check each independent variables individually. So first, you can test if there is a significant difference between mouse and touch screen. In this case, you don't divide the experience level. So you just test between the 2 interfaces, and you take all of the experience levels in each of the variables. So that's called the main effect of the interface. And you can, so in that case, the graph will be showing so the graph won't show this novice or experienced, but it will be just mouse and touch screen, and we'll have only 2 levels showing. So you can test in that way. The other graph you can think of is only having novice and experienced and only comparing between those 2. So that's the main effect of the experience level. And the interaction effect is actually a combination of 2 here. And if you have a significant difference in terms of significant level of interaction effect, and that means the results depends on the other independent variable. So such as shown here, touchscreen outperformed mouse in novice case, but it was when it was experienced users, it reversed. And if you want to check if this is statistically significant difference made, then you'll have to look at the p-value printed out for the interaction effect. So again, it all comes down to the statistical tool. So for the factorial design, we'll talk about this later, but you usually use multiple factorial ANOVA. And this, if you run this test, it prints out 1 p-value for each independent variable, and also 1 p-value for each combination of interaction effects. So you can test if the 2 independent variables interacts with each other or not. And as you can see here, the more independent variable you introduce, there are more things you have to consider, right? So it becomes more complicated of your interaction design and the study results you have to analyze. And especially in terms of interaction effects, if you have 3 independent variables, then you'll have to interpret the results of the statistics based on 3 main effects, so each independent variable separately, and then 3 two-way interactions, which is combination of 2 independent variables. So comparing independent 1 versus 2, 2 versus 3, 3 versus 1. So there is 3 two-way interaction methods, and there is another interaction between all 3 printed out from your statistical tool. So there is the number of independent variables increases, there are it becomes too much complicated, and in that sense, it's much more easier if you restrict your number of independent variables within one experiment, less to be not more than 2. So, and by the number of participants, I think we've briefly talked about this earlier when we were talking about the participants in general. And rule of thumb, again, if your design is between subject design, usually we end up with number of 15 to 20 per condition. So if you had 3 conditions, then you'll have to multiply it by 3, of course, to get the whole participant numbers. Within subject design, since each participant is trying all of the conditions, you end up with like 15 to 20 participants usually. And the smaller the effect size, which is the difference between the 2 values you are expecting, such as if you're expecting like 1 second of difference in test completion time, then compared to expecting 20 seconds of time difference, then smaller the difference you're expecting, maybe you need more people, and since it might have more chance of having larger variance between people. And in the same way, more variance between the users you expect, then you might want to have more participants to get more statistically significant results. And the more conditions of the experiment you get, we'll talk about this later when we talk about the statistical tools, but if there's more conditions, then you'll have to run more statistical tests to comparing each pair of the conditions, and that will let you require more participants needed. So in an essence, simpler is better in terms of your user study. Having less number of independent variable and less number of level in each independent variable makes it easier in terms of recruiting participants. And in a more formal way, there's also a statistics tool called power analysis, and this is a tool, and there are a couple of statistics tools, some free program such as G*Power. You can download it from here. And also this power analysis depends on what kind of study design and what kind of statistics tool you are using to draw conclusions. But usually the parameters you type in is the alpha level, which we mostly use 0.05. And the effect size, which was difference between the 2 mean values, average values, and not only the mean, but it usually requires to be divided by the expected standard deviation so that you can rule out the variance between the users. So you type in the alpha level, effect size, and also beta level, which was the type 2 error, chance of having type 2 error. And usually this is set to 0.8, which is 80% of, no, it's actually 0.2. 0.2, while this 0.8 is explaining about 1 minus beta. So anyway, you type in these values, and then it will print out how many participants you might need to have significant difference. But usually the numbers are higher than 15 to 20, unless you have very clearly different numbers typed into your effect size. So once you have your study, there are a couple of things you have to think of if your study design is valid or not. So you always check if your study is valid internally in terms of having less source of errors, random errors, so that the difference you found is solely because of the interface you've changed, independent variable you've changed. So that's checking the internal validity, and this is about making the random error sources controlled. And external validity is how these results can be generalizable. So again, this is a trade-off between how you are going to control certain variables or not. So the more you control, you will make it more valid internally because of you ruled out all of the random error sources. So that, but in that way, you might be ending up making it less generalizable because it might not reflect the actual situation where the user uses the interface. So we've been talking about random errors, which is errors introduced by chance, having different subjects and so forth. But also there is also some systematic errors, which is called bias, which is due to the wrong design of your study. So it always kind of leads the value to be pushed to having either having significant difference or having less difference due to your study design itself. And the main systematic errors that you can think of in the experiment design is due to either the measurement instrument. So if your measuring device was having some systematic errors, then it could introduce some error to your conclusion. Experimental procedures, such as if you didn't balance out the order of people trying each of the conditions, then that might have introduced some errors. And the participants themselves, if some of the participants were really tired or had some problems with their physical health, then it might have introduced some errors. Experimenter behavior could be also be an error. So if you were very polite to one participant and you were very rude to another participant, then they might have had different performance. So that could be another error source. And of course, the experimental environment, such as noise level and so forth, you'll have to control them. And to try to avoid these errors, the best thing is to do a pilot test. So you run, once you've checked, planned out your experiment, try to run your experiment so that to find if there is any problem with the instrumental problem with checking the measurements and so forth, and you can iron out those problems easily running a pilot test. The other way to avoid these problems is standardizing the procedure. So by standardizing, we mean writing down how you will run each of the participants and how you will treat the participants in what way, what order, and sort of things. So you basically write down the whole experimental procedure and you stick to that plan when you run each of them. And try to not chit chat, which is basically saying stick to your standard procedure, what to say to the participant and so forth, rather than doing it by instant idea. And while writing down this standard procedure, it might be also good to decide how to deal with exceptions, such as if the participant gets stuck with a certain task, then he doesn't know how to proceed forward, then it's better to decide how to deal with that kind of condition. Either you just quit the experiment, or are you going to give a penalty of 10 seconds and let them know, or whatever. So you'll have to better decide that in advance. And of course, and also if they have some questions, then to what level are you going to answer them should be also decided. And by having this standardized procedure also helps you having an assistant by another people to run the experiment. So if you are going to have multiple experimenters, which is, say you are running out of time and you want to run the experiment in parallel, then maybe not only you, but could be another person helping you running an experiment in parallel. So if you have a written down standard procedure, then you can easily let him stick to the procedure so that make it as similar as possible. So this is a typical example of how you run an experimental session. So first you check the system and devices, make sure everything is working. And then all the questionnaires and forms are printed out. And once the participants come, you greet them, introduce the purpose of the study, and show them the informed consent form and let them sign the consent. And then you assign the participant to the way you designed, either within subject or between subject and so forth, or random method you've thought of. And then ask the participants do the training test in different conditions. And usually it's good to have a training session before you actually do the actual experimental test, because some of the interface might be new to them. So it might be better to have them learn a little bit through a training session, so that the learning time might not affect the actual results of the experiment. So, and then once they are done, you can ask them to answer the questionnaire. Either you can design them to answer for each condition, or at the end of the whole condition, you can choose whatever way. And then usually you also do a debriefing session, which is basically an interviewing them. So to ask them if they had any problems or other. So this is useful to collect some more in-depth qualitative feedback after your experiment. And then if you said you are going to pay them or give them some incentives, then you pay them. Yep. So working with participants, it's always important to treat them politely and allow them enough time, but don't waste their time. And also important to make some breaks between the conditions. Sometimes if your study is about how stressful, physically stressful is your interface, then maybe better to have some break between the conditions, so that one condition doesn't, the stress doesn't carry on to another condition and so forth. And of course, it's never enough to emphasize on make sure you collect the informed consent and make sure the privacy and participants' right kept. And being an experimenter, writing down the instructions and checklist is easier to offload your brain. And if you need assistance, then again, written down procedure could be quite helpful. And print out the questionnaires and documents in advance. Rehearse the procedures. Again, pilot study could help. And if you find some odd behaviors or some odd things, then better make sure you write them down or mark the subject that you had, so that you can possibly, while you are analyzing the results, you find some odd results that you didn't expect it, then maybe that might be due to some odd behaviors that users had, and so forth. And of course, if you end up the experiment without the data collected, such as if you're collecting task completion time to log data, then at the end of the experiment, if you find out the log was not printed out, then that's the most thing that you want to avoid. So in terms of writing down some of those odd situations, it might be good to record the experiment, either take a photo or a video of the experiment, so that afterwards you can, the good thing of having a recording is that you can also learn after the experiment, so you can have another chance of observing people, how they do them, so that gives you another chance of doing that. Or if you find some odd things that went wrong, then you can validate it through the video recording, so that you can say this odd value was due to these things and so forth. And it's also useful for publication when you have a video clip or a picture. Of course, you have a backup. If you provide a video clip or a picture, then it's more convincing with the publication. But again, if you are going to record or take a photo of the subjects, the participants, then make sure you mention it in the consent form so that they are aware of it. So that's it. I think I ran over time a little bit. To sum up, you identified your hypothesis, specify the design of the study, run the pilot study, and recruit the participants, and run the experiment, analyze the data, and report it in your results, and then draw a conclusion, which is basically either rejecting or retaining your hypothesis and making conclusions. One thing about experimental study, although it's the most formal way to discover new conclusions, it's still limited. There could be still some limitations, such as there could be some error with the data collection method, or some other non-controlled random error could have affected your experiment study, although you haven't identified those. So you cannot really, it's always important to have multiple methods that you combine to reach to the final conclusion of your whole research. So having multiple researchers, or even if you are the only researchers, having multiple methods such as user experiment and some interview or some other observation, you line them up together and see if they all match with each other. And that's basically called triangulation. So using different measures, different objective or subjective measures, and qualitative and quantitative measure, and try to triangulate them and see if they reaches into a same conclusion. That's important. And also, a single user study cannot tell us everything about the bigger picture. So again, it could have had some random error that affected the single study. And of course, one scientific paper is not scientific truth, because it's always good to have multiple studies showing the same trend. Then that's where you can conclude that's the actual finding. And also, science is not static. Sometimes the theory evolves and they change. So one thing that was true in 1800s might not be true anymore. So might be careful of those trends as well. So those are the chapters we've covered. And next week, today we talked about how to run the experiment and how to design it. We didn't talk about how to analyze the results. So we'll be covering in the next lecture how to analyze the results using statistics tools. And actually, it might not be next week. It will be 3 weeks after, because next week is break. I think 1 week is for your thesis, 1 week is just simply break, and I think the last week is for project, 1 week project or something, assignment. And so I'll give you 3 weeks for this. So say you're planning for a user experiment for comparing task completion time of 3 drawing interface. So you are trying to compare mouse and touchpad and stylus pen and see how fast people can draw things using these 3 interface. And you also want to compare if there is any difference between experts, say artists who always draw something, and novice users who are not used to drawing. So this is the kind of experiment you are trying to plan. And the assignment is to describe your experimental design. So first of all, of course, you'll have to identify what are the independent variables. Some hints are you are having different interface and different expert level. So already 2 independent variables you can easily identify. Dependent variables, I've described what we are going to compare, which was test completion time. And then how many factors and levels, how many conditions we have, and how many levels in each independent variables are. Is it within factors or between subject factors? What would you be your hypothesis? And then what do you think your experimental task will be, and what kind of environment you'll be using? And then describe the procedure, how you are going to assign the participants, and what would be your plan, and so forth. The procedures including, would you have a training session or not? Are you going to have a break between the sessions or not, and so forth. Okay, so I'll give you 3 weeks, which is basically after the 3 weeks break before the next lecture. Okay, sorry for taking almost 2 hours.